Lesson 115 is about polygons, and then a little bit about congruence and transformation. In math, algebra half included, we call the white flat surface we're looking at right now the plane. In particular, we've encountered this word when we're graphing. We've called that a coordinate plane, which is just the square graph that we graph on. That's all a coordinate plane is. You don't have to draw anything else when you have that piece of paper. But a plane is a flat surface. A geometric figure drawn onto a plane is called a planar figure. A plane figure, basically, is what it's calling it. Remember, all math lines are straight lines that have no ends. A part of a mathematical line is called a line segment. A polygon is a closed planar geometric figure whose sides are all line segments. If a polygon has an indentation like a cave, it's called a concave polygon. This is an example of a concave polygon. See how it's got almost like a cave in there? If it doesn't, it's called a convex polygon, like that. Convex, no caves, no indents. What's wrong with calling this a polygon? I'm all done. It doesn't all connect. It needs to include all line segments so that every spot is filled. So this is not a polygon. Oops. Still not a polygon. Not a polygon. These ones are, and remember spelling for polygon. Concave, convex. Different names for polygons. Instead of drawing them all, can you just rattle them off? Three-sided polygon, triangle. Four-sided polygon, quadrilateral. Five-sided, pentagon. And it goes on and on. Check out the table on page 358 in case you ever need those names. It goes all the way up to a 12-sided figure. You know the name for a 12-sided figure? Dodecagon. I'm going to write that one down for you. The dodecagon. Now, if it ever had more than that, you just call it an n-gon, where n stands for the numbers. So let's say 15-sided figure. It's an n-gon. In this case, n is a 15-gon. After 12, you just call them things like that, or the 13-gon. Make sense? Two sides of a polygon meet at a point called a... What do we call that point in triangles and anything else? Vertex. Plural is vertices. So we're just doing a bunch of terms here. Good to know for geometry things. If I have a shape like this one, and they all have label, or how would we label it besides just calling it a 1, 2, 3, 4, 5, 6 hexagon? We could also label it by saying something like a hexagon A, B, C, D, E, and F, right? You could call it all sorts of things. You could call it, boy, I don't know, FEDCBA. You could call it EDCB. You could call it DC. There's 16 names for this thing. Now, a regular polygon, what does regular mean? All angles and sides are equal, which looks like this is indeed, equal sides, shown with tick marks. These angles are also all the same. So this is called regular. Show my tick marks. One tick mark matches with one tick mark means they're the same measure. Two tick marks matches with two. Anytime you see two, in this case, they're the same measure. The polygon with the fewest number of sides is the triangle. Triangle is called an equilateral triangle when it's regular. All the angles in an equilateral triangle are 60 degrees. 60, 60, 60. 60, 60, 60, which makes sense because how many degrees in every triangle? And divide that evenly into 3, you get 60 for each angle. Quadrilaterals are any four-sided polygons. The regular quadrilateral is the square, right? The square. How can I show that this is a perfect square? We can maybe show it with our 90-degree angles. We could also show it, make sure we've mentioned that all sides are the same. Regular quadrilateral, and so on and so forth. You see how we show things are equal, how we show things are regular, what regular means. Regular pentagon, it's good to think about how in a pentagon, forgive me for it not being perfect, let's call it regular. How many degrees are in an entire pentagon? Well, for every degree, you add up 60 degrees, 60, 120, 180, 240, 300, and 300 divided by, no, that's not right. 360, that's it. I think any closed polygon has 360 degrees in it. Therefore, each of these divided by 5 comes out to about 108. Is that right? 108 times 5? No, that's still not right. I have to check on that one. How many degrees in a pentagon? Because that one's not on here. I was just talking off the cuff there. A diagonal within a polygon is connecting two opposite vertices like this. Oop, jeez, like that. Two non-consecutive vertices, so they can't be next to each other, or else it would just be another side. Those are all diagonals. Trapezoid is exactly two parallel sides, four total sides, but not a square, right? So let's just get rid of all sorts of things here. That's the slow way to do it. Let's do it like this. And trapezoid, this isn't going to be very regular, but trapezoids, usually we think about this one. What are my parallel sides? Top, bottom. Four total sides, but these going in opposite directions would eventually intersect if they went on forever. Terms like rectangle, rhombus is a parallelogram that has four sides of equal length. So a square is an example of a rhombus, but a rhombus doesn't have to all have 90-degree angles. So it could include just any parallelogram like this one, where these equal a measure and these equal a different measure. Those are the obtuse and these two are the acute. This is a rhombus parallelogram if all sides are the same. Rhombus. Keeping all this straight can be tricky. You might just have to reference this lesson 358, 359 to remember all these terms. To finish, congruence, right? It's congruent if the measures are all the same. So this is a perfect copy. It's definitely going to be congruent. Same shape and same size. Geometrically equal, except maybe position or orientation. Position means where it is. So that's positioned here, but this is positioned over here. They're still congruent, but they're positioned different. What about orientation? Orientation means it's still congruent despite me maybe rotating it. That's called rotating. I'll rotate it all the way back now. Translation is simply taking and being somewhere different, changing the position. Reflection is flipping it. So flip, maybe even flip again. See, this is still congruent with the other one. It's just been flipped and also translated. These are all examples of what we call transformations. I have been transforming the shape. It's still congruent. Still congruent. When using transformations to place one figure on top of another, many combinations of transformations will work. Other ways to look at these three that I've given examples, translation, rotation, and reflection, are all on page 360. Why don't you do, pick 4 practice problems, do at least one from each section, and show me those. Problem set for Tuesday.